Right? It's always, I have 312, then 116, then 312 back to back. So it takes a second for my brain to go, we're not talking about array lists and hash maps now. We got to talk about HTTP. All right, so let's get back into 312. Today we want to talk about HTTP, which is the first protocol that we have to code. This is in a pretty real way where the course really starts. This is the first content that you will have to code. That's arguably on Monday that was true because it's front-end stuff, but I give you most of the front-end stuff. You really don't have to do your own front-end from scratch until the project, which is a group project, so you divide the work and everything. It's not fully on you. But today, HTTP, this is where you all, right from Objective 1 of Homework 1, need to code. We saw last week TCP and IP, and these were two protocols that make the internet useful. IP just is the internet. That's how the internet works, but it drops packets. It's not reliable, and TCP adds that reliability. So when we send a message over the internet, if we're using TCP IP, we know that message is going to get to its destination. We can be sure that whenever we're sent a message, our server gets sent a message from the browser, we're going to get the entire message intact. And when we send a response back to the browser, that browser is going to get that whole message completely intact. All the sequence numbers and drop packets, all that stuff's already been handled for us. That happens in the background. We don't have to think about it. And I actually remembered today, finally. Just a quick logistical note. There are two sections. I kind of just mentioned this, but at 2 in NSC 225, and then 4 right now, right here, 4 o'clock in this room. I don't care which one you go to. If you want to go to the other one, if that works better for your schedule, go to the 2 o'clock in NSC 225. That's fine with me. I usually prefer the earlier one. Plus, we have a massive room with the same amount of enrollment. So we have tons of room, like physical room in the room, too. So if you want to go to that one, I would actually like it because then we would be able to relax and spread out a little bit more in this one. But either way, whatever you want to do is up to you. So TCP IP, this is all taken care of for us. We're going to use libraries for this. Well, one specific library, socket server. It's in the starter code, in the handout code. It's already there for you. That's going to handle TCP and IP. Well, TCP, IP is handled at a lower level, at the OS and hardware level for us. But all that's going to be handled for us. So we just start thinking in terms of HTTP, and we just assume IP and TCP are doing their job really well, and we don't have to think about it. But it's nice to know where we're coming from. This is the foundation that we're building upon. And when a packet is going through the internet, it's going to look something like this. This is a very simplified view of the network stack. But we're going to have the IP headers. At the top, the first bytes of every packet we send are going to be the IP headers. The routers of the internet are going to read those. And when, by the time a packet gets to our device is going to read the TCP headers and start stripping out the IP headers. We're done with those. Once a packet makes it to our device, we don't care about the IP headers anymore. Our device is going to read the TCP headers. It gets all these packets. There's the sequencing number, the request drop packets, re-request them, all that kind of stuff, and do all the TCP stuff, and then assemble the entire message back together. Piece all of these sequence numbers together, all these packets into one message, remove the TCP headers from all of those packets, and then take this one overall message and send it to our process, our server, which is one process running on our device. It's going to get that message with no IP headers, no TCP headers, and all sequenced back together. And the first thing we're going to see are HTTP headers, and then finally the content, what's actually being communicated using all of these protocols, what the purpose of what we did all this for. So in our code, we're not going to ever see IP or TCP headers, but we will see HTTP headers, and that's the first thing that you'll have to parse and decode and understand. So that's where we really start with the homework code, or as web developers in general. That's where it all starts, is HTTP headers. HTTP, specifically HTTP 1.1, is defined by RFC 2616. There's actually a newer one that supersedes this, 2616 defines everything that we'll need for this course, so I still like that one. But if you want to look at the newer one, it's fine too. RFC, request for comments, is a document, a set of documentations of the RFCs. There's RFCs defining pretty much every protocol for the internet. Can I just say every protocol for the internet? All the really foundational, fundamental protocols of the internet that we have to agree upon, they're defined by RFCs. So if we need to agree on a protocol, there's got to be an RFC for it. If the browser has to code up HTTP, our servers have to code up HTTP, and as long as we're both following the same RFC and we're coding to spec, then we're going to have effective communication over the internet. But we have to be following the spec. The spec has to be defined somewhere. For HTTP purposes, that's going to be RFC 2616. These RFCs are maintained by the Internet Engineering Task Force. They're the ones that kind of control the RFCs. Control is a bit too strong of a word, but they're responsible for maintaining the documentation, and then everybody can create documentation. They can request for comments, create documentation, and then as those RFCs get adapted, then they start getting more widespread use, like HTTP did, like IP, like TCP. They'll have RFCs to define what those protocols actually are. And for our purposes, specifically sections 4, 5, and 6, every section is useful. You're going to find some good juicy bits in there. But 4 is going to specify the format, the generic format of a message, an HTTP message. 5 specifies requests specifically that come from the browser to our server. And 6 is specific stuff for responses from our server to the client, to the browser. The RFC is the ground truth for the protocols. So even to the extent where if I say something in lecture that contradicts the RFC wins. The RFC is the ground truth. That is what the protocol is. No matter what I say, no matter what someone on the internet says, no matter what someone on Stack Overflow says, doesn't matter. The RFC always wins. It is the ground truth. That is the best resource to go for any questions about any protocols. So if you ever have a question, you're coding your homework, and you're like, I don't know what I'm supposed to do in this exact situation, somewhere in this RFC, or maybe a supplemental RFC too, is going to have your answer. Somewhere in there has to be your answer. So that's your be-all and end-all resource. That is the ground truth for everything. It's the RFCs. And HTTP is an application layer protocol. This is network terms. We're not going to talk about the network stack too much. We're going to get to HTTP and just kind of hang out there for a long time. But if you talk about the network stack or you take modern networking concepts, you're going to see the stack. We saw a simplified view of the stack earlier. But this is an application layer protocol, which means our applications, which I've been calling processes, our processes actually care about this protocol. There's nothing handled at the OS level. There's nothing handled at the hardware level. Nothing handled at the networking infrastructure level. This is all has to do with our process. In this case, a web server. Our web server code cares about HTTP. So our applications care about this protocol, and it's up to our applications to implement the protocol. Nothing at the OS level, nothing at the internet level, the IP, TCP, none of that even cares that it's communicating HTTP messages. They just don't care. Why would they? They shouldn't. It's our applications that care. That's why it's an application layer protocol. And it's almost always going to be, I say almost, but I'm really just hedging there. It should always be communicated over TCP. There's some wacky scenarios I could think of, like HTTP doesn't necessarily even have to use the internet. You could implement HTTP just by writing out a note and handing it to somebody. You could implement HTTP like that. That'd be fine. But realistically, in the real world, it's always going to be over TCP, so we can have reliable messages, meaning we don't have to worry about drop packets and all that stuff. So we have reliable communication between server and client through TCP, and IP is handling the transportation of those packets. So we just worry about the contents, which is HTTP. And this is what we're going to use to, I kind of implied it a few times, but this is what we're going to use for our web servers to host our web pages and eventually web apps once we add some dynamic functionality to them. This is the protocol we're going to use, and as long as the people writing the browsers and maintaining the code for browsers and we both follow the protocol, we follow the RFC, study up, and make sure we're compliant with the protocol, we're going to have effective communication. We're going to be able to host our websites effectively. If something's wrong at the browser level, that's not our problem. They got to fix that, and any modern browser is going to implement the protocol correctly. And then any issue at the server level, if we don't implement the protocol correctly, things going to break. We're not going to be able to host our web page. We got to fix that. This is a request response protocol. And this is going to have a lot of implications throughout the whole semester whenever you use an HTTP. But what this means is the client, usually a browser in our case, it won't always be a browser, but for these early lectures, I'm always going to say browser. The browser is going to send a request to our server, an HTTP request, and we're going to respond with an HTTP response, and that's it. It's all we can do. And that's just how HTTP works. The browser is going to send us a request. We respond with a response, period. We cannot send two responses after one request. We can't just send something to the browser whenever we want. We have to get an HTTP request, and we respond with one HTTP response, period. That's how HTTP works. It's a request-response protocol. We cannot respond without a request, and every request should have one response. And we usually have a lot of requests to be able to host one site. If you, we'll do it quite a bit throughout the semester, but I don't know when the first time I'll have a chance to do it is. But if you go to your developer tools in your browser, which I usually call the browser console, go to the browser console, go to the network tab, and refresh the page. And every single line you see there is one request response using HTTP. And you can see that there's going to be dozens of requests and responses to host one single web page of one website or web app. It's going to be dozens of requests for any modern site these days. Any complicated. Obviously, I shouldn't say obviously, but actually, no, I don't even want to say that. It's going to be dozens of requests for most sites that you visit these days. So more than one request response. We can't get everything done with one request response. Technically we could, but it's bad, terrible practice. And a web server, I mentioned like hardware versus software. For the rest of the course, whenever I say web server or server, I'll just say server because we're always talking about the web in this course. I don't have to specify. I'm always going to mean the software variety. So a web server is software that speaks HTTP. It's going to listen for HTTP requests and respond with HTTP responses. So right from Objective 2 of Homework 1, you'll start coding your server to listen to HTTP requests and code your server to respond with the appropriate HTTP response. I talked about front-end and back-end. I used to do this lecture before the front-end lecture, but since it's reversed, I don't really have to talk about the terminology here. We already talked about that between back-end and front-end. And this is what it typically looks like to load a single page. The browser is going to request our HTML from the web server across the internet, across the network. It's going to send an HTTP request and say, give me your HTML, please, for your home page. This is the first communication. And the server is going to respond with the HTML for the home page. And that's it. End of transaction. It's a request response protocol. That's all we're going to do. We got a request for our HTML. We sent our HTML. Done. Job done. The server can rest and relax after that. There's a lot that's missing there. So this request response protocol seems pretty straightforward. Okay, somebody asks us for something, we're going to give it to them. But there's a lot missing there. There's no concept in your code, in your server, in any web server, there's no concept of, oh, this person just requested my HTML. I bet they're trying to visit my entire page. They're probably going to ask me for some CSS, some JavaScript, some images. They're probably going to ask me for all this stuff. I got to be ready for that. Maybe I just preemptively send them all that stuff. No, we don't do any of that. They ask for the HTML, respond with the HTML. We keep it as simple as possible. And we completely forget that they asked for the HTML. Then the browser is going to get that HTML, scan through it, say, oh man, looks like there's a linked style sheet, there's a couple JavaScript files, there's some images, there's a movie I got to start buffering. I got a lot more stuff that I need to get. So each one of those pieces of information is going to be another request. The browser is going to go back to the server and say, hey, I would like to request your CSS, please. I would like to request your JavaScript. I would like to request this image of an eagle. And the web server is going to get each one of these individual requests and respond with an individual response. Server's sitting there and says, oh, somebody's asking me for my CSS. Here's my CSS in a response. Somebody's asking me for my JavaScript. Here's my JavaScript. All we're doing is responding to individual requests, and it's the browser's job to take all of our responses, smash them all together, and render an actual web page. The web server has no concept of that web page being loaded. For all it cares, when it gets the HTML request, the CSS request, and the JavaScript request, for all it cares, all three of those requests might have came from different people. The server doesn't care that it was one individual user requesting all of those things and loading up their web page. It doesn't care. So when we're coding, there's nowhere in your code where you say, oh, somebody requested my HTML. I better get ready for a whole page load. Nope, you just respond with your HTML. Don't overthink this one. You just respond with your HTML. You get a request for JavaScript. Somewhere in your code, you're going to say, if I get a request for my JavaScript, send the JavaScript. You don't have to do anything else. It's up to the browser to smash it all together. All right, for HTTP requests, there's several different types of requests or request methods that we're going to talk about. GET is all we'll talk about today. We won't get to POST today. I'll define them on the next slide, but we won't go into all the details of POST yet. We will, don't worry. Don't you worry, we'll get to POST. But GET, POST, PUT, delete, and maybe head. I don't know if I'll cover head this semester. Maybe I'll at least mention it, but I might not even do that. I might have scrapped the lecture, I forget. When we talk about cross-site request forgery, is when we would talk about head. I got to talk about it. It's too interesting to not talk about. But anyway, we'll talk about all these in due time with possible exception of head. But we will talk about GET, POST, PUT, and delete. For Objective 2, Learning Objective 2 on Homework 1, it's all GET requests. When we get to Objective 3, Learning Objective 3, you have to handle some PUT requests. And then for the AOs, we're going to sprinkle in some... Did I say PUT? Post. If I said PUT, I meant post. And then for the AOs, we're going to sprinkle in some PUT and delete by the end of the homework. So the first four here are all present on Homework 1. So GET is, as the name implies, when you want to get information from a server. Every example that I've given so far has been a GET request. Get me your HTML, get me your CSS, get me your JavaScript, etc. Those are all GET requests. You're requesting information from the server. So we want to get some information from the server, we'll send a GET request. If we want to send information to the server, so this is when you're filling out a form, maybe it's a login or registration form, you're uploading an image, you're sending a chat message. Whatever you're doing where you want to send information to the server, you're going to make that a POST request. So you're going to send information to the server with a POST request, and this will have a body in the request in addition to headers, but we'll talk about what those mean when we get to the nitty-gritty details. And URLs, I don't think I have to specify what a URL is. You've used them your entire lives. But let's break it into its parts to specify exactly how a URL is structured. And it's in these pieces. We have the protocol first. For our purposes, in most of the class, the protocol is going to be HTTP, but we will have some other protocols later on. We'll have WS, and then HTTPS and WSS, the secure versions of those, where WS is WebSockets, the secure version of HTTP, and the secure version of WebSockets. So protocol, colon //, then host colon port. Host is the IP address of the server you want to connect to, or its domain name, or some special reserved name. We'll use localhost for a lot of our testing purposes, which is the IP address of your device, which is a special name for that IP address, which I Oh, no, I'm blanking. I think it's 127.001, maybe? It's something like that, is what localhost maps to. And then :port, what TCP port do we want to use to connect to that host? For our purposes for the homework, you're going to listen on port 8080, so you would do localhost :8080 to be able to connect to your server. If the port is not specified, the port is optional. If it's not specified, you'll use whatever the default port is for that protocol. For HTTP, that's port 80. For HTTPS, that's 443. So on just navigating the internet on your day-to-day lives, you're never going to do :port because all deployed websites are going to use the default ports. But when we're developing, we tend to use these higher number ports in our development environments to avoid port collisions and the like. It makes it more convenient to test our code if we're using something like 8080, because something else on your device might already be using port 80, port 443. We're going to avoid that and just choose some large number and use one of those ports. Then the path is the specific resource you're requesting. So a specific host, some website, some domain name / whatever, that's the specific thing that you want to get from that site. I think that one's pretty, not self-explanatory, but something you've been using your entire lives. I don't have to explain. And then we have two optional parts, something you might not have thought about so much as a user of the internet. The query string and fragment, which are both optional. If there is a question mark in the path, anywhere in the path, what follows is going to be the query string up until a hashtag, if a hashtag is present. The query string is any number of key value pairs, each separated by an ampersand, and the key and value are separated by an equal sign. All strings, of course, that goes without saying, right? All strings, so if I have question mark Q, I have a variable Q set to the value web development, and that's the query string that's being sent. And any major search engine uses this protocol. When you type into the search bar, what it actually does is formulates a URL for you with your search as part of the query string, and any extra parameters you want to add to that, it's going to have, say you want to do an image search, DuckDuckGo will create this IA variable equal to images, and it'll send that query string to their server as a GET request and then respond with your search results. Then fragment, this is useful if you want to navigate to a specific portion of a page. So if I want to go exactly to the definition section of the Wikipedia page for URIs, I add that hashtag there, and when I go to that link, it'll automatically scroll to the definition section. So this can be handy, especially if you're like sharing links with somebody. This works with PDFs as well. If you want to share a link, I've had this situation before. I want to share a link of a PDF that was hosted online that was like 400 pages, and I want to show somebody page 231. I don't want to send them the link and say, scroll to page 231, and you'll see the funny thing I'm talking about. If you use a fragment, browsers work with hashtag, I forget the exact notation. I think it's hashtag page and then the number, or just hashtag the number, the page number, and it'll automatically scroll when they click that link, scroll to the page that you specify. You can send them a link directly to a certain portion of the content of the resource that you're sending. So it can be handy for navigational purposes. And HTTP is stateless. So HTTP is a request-response protocol. The only thing we get is the request, and then we send a response. We can't look at other information, at least the protocol itself isn't coded to do this, to have any other information related to that request. So unlike TCP, where we establish a connection and there's multiple IP packets for a single connection, we don't do that with HTTP. There's no, okay, you sent a request for my HTML, let's start a session here because I know you're going to request the rest of my website, and oh, it looks like you didn't request the JavaScript, and I know you're going to need that, so let me send. None of that. A request, response, end of transaction. We don't have anything else associated with that. So there are ways that we kind of pretend that HTTP has some sort of state, because if the internet was completely stateless, that would be kind of crappy. The internet would be way less interesting. The biggest, most fundamental thing we need state for is to log in to anything at all. Like when I send a request, I want the browser to remember that I'm logged in, so I don't have to type my username and password into every single every single thing that I do on their website. I'm not going to use that site. So we use cookies for that and many other reasons to be able to remember something about each user. We still only get that request, but that request has some identifying information. We take that identifying information, go to our database, look up who this user is and anything we need to know about them, and then use that extra information to handle that request. It's still stateless at the protocol level, but we kind of pretend that there's some state added to it through things like cookies. And new lines. I need a whole slide to talk about new lines, and I'll talk about this quite a bit in all semester. New line characters. A new line in HTTP is represented by /r/n. It's two separate characters to formulate a new line, to represent a new line. This is very important. If you don't represent your new lines like this, your server won't work. And if you get a request and you have all your request parsing code and you don't handle your new line characters like this, you're not expecting this, your code's going to break. Things aren't going to work the way you want them to. If you disable cookies, does the browser not know what your IP is? The browser will still know your IP address if you disable cookies. Because is that necessarily true? The browser could know. The browser doesn't get the IP headers, so it doesn't have your IP address there, but it would, I believe it still retains that information. It'll still know at the browser level. But disabling cookies does not hide your IP in any way, for the short answer. If you disable cookies, you won't be able to log in, though. /r/n, this is a really old, this is kind of an artifact of the old days, way before my time even, is we used to have typewriters. You know, you'd actually type and there'd be arms with ink on them, would slam the character onto the piece of paper. You would type and there would be a carriage that goes across the paper. Every time you hit a key, the carriage would slam down the character and move over by the width of one character. So you're typing, and this carriage is going across the page. Gets to the end of the page, you have to perform two actions to move on to the next line. You have to do a carriage return, get this carriage back to the beginning of the line, and then a line feed, you rotate the paper down to the next line. So it's two actions to be able to get to the new line. So this was started from the days of typewriters, kind of from those old days. And it just stuck. And HTTP, I mean, it's an old protocol. Typewriters were still a thing when HTTP was created. So this made sense. It doesn't so much now, but we're stuck with it. It'd be a huge undertaking to change the entirety of all of the internet, not necessarily the internet, but all of the web. I think that's fair to say. All of the web to change their new line characters. It's just not going to happen. So we're stuck with this as our new line characters, /r/n, which I'll usually say CRLF, which is our carriage return line feed. CRLF or /r/n, I mean the same thing, but your new line characters have to be this /r/n or CRLF. Has to be. That is part of the protocol. The browsers are expecting this. So if you just do /n for your new line characters, the browser's not going to know how to interpret your responses. And if you're just saying split on /n in your parsing code, all of your lines are going to have this trailing white space of a /r, and that can break a lot of your parsing code if you're not expecting those /r's to be there. So we do have to be very aware of our new line characters, /r/n. These two characters, this 2-byte sequence is very important in HTTP. This will be important throughout the entire semester. We always have to be aware of this, for better or worse. Well, for worse. It's for worse. But we do have to be aware of this. Browser still knows cookie only stored data client side. Well, technically IP is tied to your router and other stuff. Incognito is not private either. Disabling cookies and going incognito, the sites you're connecting to still know your IP address and port number. I mean, port number is less important, but they know your IP address still. That's why we use VPNs. That's why VPNs are still a big industry, because that's how you would hide your IP address. How will the site retain info about us? You won't have to log in every time because, I don't know, some sites allow you to skip login even if you disable cookies. That I'm not so sure about. If you disable cookies, you shouldn't be able to log in. That site might not be disabling all cookies would be my best guess of there. I don't see how else they would let you skip the login without cookies. I mean, they could potentially tie your login to your IP address, but that doesn't work. It just doesn't work. Every time you switch networks, like going from here to home, you would have to re-log in, and anybody else on your network, if you're at home and you're behind I just forget the blank on the name for this, but if you're behind a router that has one public IP address, then everyone at your house will be logged in as you. It's just so many security risks and UX reasons not to do that. All this talk of cookies is making me hungry. It's almost always optional cookies. That makes more sense. What's the difference between post and put? I will talk about this next week or 2 weeks ago, so I'll give you a short answer here. A put has to be idempotent, meaning if you send two identical put requests, it'll be the same as if you just sent one put request. But a post request is not idempotent. So if you send two identical post requests, there will likely be more action. So like sending a message in chat, if you say the same message, type the same exact message multiple times, that's a post request, and you do want additional action to happen when you send multiple messages. But if you want to update one of your posts, and you send that would usually be a put request. You want to update your post, and you send two put requests. I want to update my post to this, and you send an identical request. I want to update my post to this. The second request won't have any effect on the data stored at the server. It'll still just be that as if you sent one change. So that's the difference between them. And there's no magic there. It's just what we agree those two words mean. So if you say, hey, here's an endpoint, it's a post endpoint, and this endpoint is a put endpoint, what you're doing is communicating that the put one is idempotent and the post one is not. But there's nothing in the protocol that enforces that. It's just something you really, 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 really should do when you're writing your APIs. So that's my short. That got a little long, but that was my short answer. Okay, so let's take a look at our first GET request. And this is what you'll get. When you're writing your server, you're going to listen for client messages, and this is what you'll get as a sequence of bytes, a message that looks something like this. This is a little simpler than the ones you'll see, but the same amount of coding complexity. You'll just have more headers, and the headers will be bigger values, because the browser sends lots and lots of headers, but that won't fit on the slide. But this has all the structure that you'll need to parse. You'll get a sequence of bytes. You have to interpret it using HTTP, your understanding of the protocol, and write code to parse a request like this, and then respond with an appropriate response. So let's break this down. Before that, I want to show you the white space characters. There are new line characters here. On the slide, I'm going to render the new line characters as actual line breaks for human readability, for visibility. But every line break is a /r/n, including a blank line at the end. The request will end in /r/n/r/n. So I'll usually say CRLF because it rolls off the tongue a lot better. So the request ends with a CRLF, so an empty blank line. And that is critically important. That has to be there. If that's not there, the whole internet lights on fire. Everything breaks. We need this blank line. So when I do render this human visible, this blank line at the bottom is not a typo. It's not a mistake or anything. There is an empty line at the end of a request. And it's very important that it's there. And we'll see that throughout the semester. But the short answer is, and throughout this lecture, which I think I'll have to finish these slides on Friday. I don't think I got through them in the other lecture either. And I'm not on track to do that here. But that new line has to be there. That blank line says we're done with headers. And then after that blank line is going to be the body of the request, and there's no body of GET request, so we don't have to think about that quite yet. Yeah, I definitely didn't get through these. I didn't get through any response slides. So as long as I get there in this lecture, we'll be even with the other one. So what is all this information? So the first line of a request, the first line you're going to read, so everything before the first CRLF is going to be the request line. So in your code, you'll say, look for that first CRLF, or what a lot of y'all do will split on CRLF, which can cause issues. We'll talk about that in due time. But when we get everything before the first CRLF, that's going to be the request line, which has 3 values separated by a space, separated by spaces. These values cannot contain spaces. The HTTP protocol in the RFC says you cannot have spaces in any of these values, which is super convenient for us. And the reason why that's part of the protocol is we get everything before the first CRLF, we split on spaces, and we know we will have exactly 3 values. If we don't have exactly 3 values, then the browser did something wrong, and we can file a bug report with Google or Firefox and say, hey, fix your stuff. But that's not going to happen. The modern browsers, the bugs are mostly gone. Or much, much more obscure than messing up the request line of an HTTP request. So we have 3 values. The first value is the request, I call it request type, but the HTTP method is the better name for these, or the request type, whether it's get, put, post, delete, head, whatever it is, options, whatever request type this is, and now I'm saying request type. Whatever HTTP method we're using, in this example, a GET request, that's going to be the first value before the first space in the request line, the very first thing that you'll parse. Next, surrounded by spaces, is going to be the path. This is, I say the path here, and I'll continue to say the path, but it does include any query string and fragment if they are present. So it's everything after the host and port in the URL is going to go right here in the request line of your request. This is just a request for slash. This cannot be an empty string, so if you just type cc312.com and hit enter without typing any path, you'll get slash, which we call the root path, which is usually where you host your home page. You're going to host the HTML of your home page at just slash. And in Objective 2, in fact, in Objective 2 of Homework 1, we're going to follow that convention. If you get a request for slash, you're serving up index.html at that root path. And then finally, the HTTP version. This is always going to be HTTP/1.1 in this course. We're always going to use HTTP version 1.1. And just because I got this question, it kind of caused some headaches for a student last semester. The HTTP version in Objective 1 of Homework 1 should be the full string here, HTTP/1.1. I had a student who set that variable to 1.1, and then it caused some issues on the grading side. And we got it resolved. I gave them credit for it. But this semester, since that'll be auto-graded, the auto-grader is going to say your stuff's bad, and you have to find that and fix that. It's going to be HTTP/1.1 in that variable in your request object in Python. So be sure you have the whole string. Don't just put 1.1. So will we be using server-side rendering in this course? It depends what you mean by server-side rendering. We will render HTML templates server-side, yes. We won't be rendering anything visually, any visuals. Actually, that might even be a lie. We won't ever be combining HTML, CSS, JavaScript. We won't ever be combining those server-side. I don't think any server does that. But the browser will be doing that. But we will render some HTML templates server-side. Right from Homework 1, actually. If you look at Objective 2, there is a spot, there's a placeholder in the HTML that you'll have to replace with the visit counter to say how many times this particular user visited the site. It's a very basic thing, but it is HTML rendering server-side. So right from Objective 2, you will be doing it in that sense. But it depends exactly what you meant by the question. What about the patch requests? We won't talk about it in this class, but yeah, it's another request type. What does it mean by request line has 3 values separated by spaces? We have the HTTP method, a space. That space character is part of the protocol. It says that space has to be there. Then the path. Then another space character that has to be there according to the protocol. And then the HTTP version. So those two spaces have to be there, which makes it feasible to parse this. We just split on spaces and we got ourselves 3 values. And we know the first one's the method, the second one's the path, and the third one's the HTTP version. So it makes it much, much easier to parse as long as everybody's following the protocol, which the browser sending us these requests will follow the protocol. In that request line, that path can be much longer than just slash. On the left, we're requesting the home page. On the right, we're requesting this specific set of slides to get these HTTP slides. I don't know if it's still 1_2, but it's still the HTTP slides. That whole, everything after the host import, all of that goes right in your request line. Even if it does have a query string or a fragment, it all goes in that request line. I think everything else on this slide I already said. Whoa. I don't know if my brain can parse this one. So when you're requesting, are you actually going to the website or just collecting the data in the site? I'm not quite sure what the question is, but I'll take a stab at this one. So when you go to a site, like in the browser, you type CSE312.com, your browser is going to send this GET request to the server, and the server is going to respond with an HTTP response containing the HTML of the home page for that server. So that's what, when we say we go to a site, that's what's happening in the background. The browser is sending this to the server parses it, does all the stuff that we're going to code on the homework, and sends the HTML as a response. And then your browser gets the HTML, starts reading that, figuring out what additional requests it needs to send, gets all the responses from the server, and then starts rendering the whole page. But this is what the browser sends to the server when you click different links. So like when you click the slides link for these slides, this is the request that your browser is going to send to the server. The headers will be different. Of course, these are just example headers, but the request line is going to be that. Speaking of headers, let's talk about headers. So headers is the next portion of the request. There's the request line, and then any number of headers separated by CRLFs. So we have the request line, CRLF, then any number of headers, each on their own line, separated by CRLFs, and then CRLF at the end, that blank line that indicates we're done with headers. I've specified all the headers I want, but we can have any number of headers, so we need some way to say, that's it, no more headers, and we do that through the CRLF. That's why that needs to be there. If you don't have a CRLF there, and you send something to the browser, you send a response to the browser without that CRLF, browser's going to hang because it thinks you're sending more headers. So you need that there to say, we're done with the headers. So headers are in this format, one per line, name, colon, value. Key value pairs has to be all strings. I think that might be self-explanatory at this point. I don't know, but they're all strings. And it's not too much more I have to say about them. That's what they are. Each header is going to mean different things. We're not going to talk about the meanings of the headers at this point, but I have a header named host with the value CSE312.com, a header named connection with the value keep alive, a header named accept language with the value English, US, and English. And what I do want to talk about is this little guy right here. This little guy can cause quite a bit of issues. So let's talk about this space right here. According to the protocol, look up in the RFC, and it's going to talk about this white space, and it says, it can be there. There might be a white space there, but there might not. And leaves it up to us coding the servers and browsers to decide if we want a white space there or not. If it's not there, then we go right into the value. If it is there, we need to strip out that white space. The value of a header cannot start with a space character. It's not allowed. So any space characters that are present there need to be removed. We need to strip out this white space. So when you're parsing your headers, If you're splitting on colon, make sure whether or not this space is here that you remove it, which handy in Python, we have the .strip method for strings. Called .strip, it's going to remove any lead